So welcome to the next of our series of lectures. As always, I would like to thank our sponsors, Jose Andres, who actually talked here a week or two ago, Think Food Group, Alicia for both financial and intellectual help, Montferrand, Whole Foods on River Street, which supplies all the food and all the lab supplies because we eat our labs. Fusion Chef by Julabo supplies the immersion cookers, and the bank from Catalonia, some extra support. We have, looking forward, on the 31st, we have Karma Ruscadella, who has a wonderful restaurant near Barcelona, and she's going to tell us something about browning. On the 7th, I think, which is the next one. Next slide. Yeah, on November 7th, Dan Barber from New York, Reclaiming Flavor. And then tonight, sorry for the slides. Tonight we'll have Wiley Dufresne from WD50. But before we do that, we're going to have a slight change in our science talk, and we're going to have a real expert talking about it, not me. So we're lucky. We have Greg Verdine from the Department of Chemistry, who will do the introductory science lecture this week. Greg.
Well, thank you very much. I usually teach organic chemistry mostly to pre-medical students in this classroom, and it's in the combination of the blood red chairs and the very difficult subject matter, I think, tends to instill fear in the faces of that I'm used to looking out to. So it's really great to see all of you looking very happy, and I don't see any fear at all. I think you're looking forward and saying, holy mackerel, Greg looks kind of scared. I haven't given a lecture to the general public for, 10 years or so, so it's really, really a privilege. The last one that I gave was here in the Science Center. I should tell you, since the head of the Charles was this past weekend, I have a particularly fond memory of this classroom, and it was the last class of organic chemistry before the head of the Charles regatta, and I was up here talking about some esoteric subject in organic chemistry, and through the back door right over there came an entire bevy of streakers from Yale University. Now, it just so happened that that class, like this one, was kind of oversubscribed. And there were people lining the entire stairway, all the way up to the back of the classroom. Those of you who are familiar with streaking know that the point of streaking is to move fast. And I dare say the Yale students didn't move fast. And they left organic chemistry humiliated even further. So that was really special. So today, what I'd like to talk about for the next 20 minutes or so is to try to give you a primer on proteins. And the problem that I have is I work on this subject every single day of my life. So if I lapse into jargon or if something's not clear, I would encourage you to raise your hand, and I'm sure you're not the only person who's wondering what the other person is thinking. So I'm happy to have this be as conversational as possible. And if, as I tend to do, is look down here to the first few rows, and I'm not calling you up there, just please yell out, and I'll get to your question. So proteins are obviously a major source of nutrition. Humans, over the course of evolution, have lost the ability to make 8 out of the 20 amino acids. We can only synthesize from simple precursors 12 of the 20 amino acids, and that means that we have to get the other 8 amino acids either from the breakdown of proteins in your stomach by acidic digestion in your stomach, or by bacteria that reside in your digestive tract. It turns out that the bacteria that reside in your digestive tract are really master constructionists of all kinds of things, and they're able to supply us with the amino acids by synthesizing them from simple precursors. Shown on this slide are a series of different proteins that are of relevance to food, and I'll go through several of these and give you some idea of why they're of interest. What proteins are doing for the most part in biology is they're the real workhorses. They're the doers. They're the constructionists. They make stuff. They're also the building blocks of many cellular components. If you look at muscle, most of muscle is protein, and that protein is doing stuff. It's contracting, it's moving. Proteins are the things in the cell that do what's called signaling. So if something happens on the outside of the cell and the inside of the cell needs to know that it's happening on the outside, it's proteins that are transmitting all of that information. So they're the information carriers. So they serve a really important role in biology. With respect to food, this protein is called hemoglobin, and it has a red color because it has an iron center in it. It has each hemoglobin protein has a single atom of the metal iron, and that iron turns out to be red colored. And of course, this is an oxygen carrier, so in highly oxygenated tissues like the brain, tissues like muscle, that are consuming a lot of oxygen in order to do work, these have a lot of blood supply and therefore have a lot of hemoglobin, and it's for that reason that they're red. Also shown here is casein. The purpose of milk in mammals is to emulsify nutrients, primarily fat, but also proteins as well. And the problem with fat is that it doesn't dissolve in water. So there'd be no way for a mother to transfer nutrients to her offspring without emulsifying the nutrient fat, which is obviously a high-calorie nutrient. And it's casein that does this emulsification. Albumin is a constituent. It's actually the most predominant protein in our bloodstream, where it's used to carry fats and carry other molecules. And in eggs as well, albumin is the major constituent of the whites, where again it's used to as a storage depot for nutrients. And renin, as you'll see, this is a protein that's made in the digestive tract of cows and other animals as well, and it's used to break down casein that's produced in milk. It's used to break down all kinds of things. And in cheese manufacturing, this is used essentially as a manufacturing component to break down casein to produce cheese. So let me tell you a little bit about I know you've all heard about proteins. I want to give you just a quick primer on what a protein actually looks like. So proteins, first of all, are linear polymers. So what this means is that they have a structure that can be thought of as being like beads on a string, where if you could start right here and walk along the central chain of a protein, you would keep repeating the same, you would keep experiencing like Groundhog Day, the same thing over and over and over again as you walked along the chain. So it's a repeating polymer. And the repeating units are actually amino acids, the thing that I just mentioned a moment ago, that there are 20 primary amino acids that are used in all organisms on Earth. Now, in terms of chemical structure, when a protein is made from amino acids, those individual amino acids become linked together. They become linked together through strong bonds that are called by chemists covalent bonds. These bonds are so strong that they don't undergo just spontaneous breakage in a way. The proteins were known for 50 years before anyone was patient enough to be able to measure one of these bonds undergoing a breakage. So they're extremely stable under ordinary circumstances. The bond that I'm referring to is right here. It's called a peptide bond or an amide bond, and I only mentioned it. It will come up later, and it links the amino of the amino acid to the acid of the neighbor next door. So it goes amino to acid, amino to acid, amino to acid, repeating unit, building up a chain. Now, if you saw only this, you'd think that every bead on the string is identical, but in fact, that's not the case. Amino acids are different from one another. And what differs are these green things that project from the main chain, the repeating chain of the protein. So there are groups that dangle off of this main chain and that give each protein its very, very characteristic structure. So you can think of these as the decorations. Think of a chain that has not one type of bead, but has 20 types of beads. Now think about the combinations. If you have 20 beads, let's say here, and you have 20 there, that's 400. And then you have 20 in the next one, that's 8,000. There are a huge number of different possible structures of proteins. And what we know is that in evolution, the entire biosphere has sampled only a tiny, 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 infinitesimally small fraction of the entire possible universe of all proteins. So when you read science fiction and you learn that, well, we might go to another planet and find a life form that's based on silicon, that's kind of unlikely. It's very unlikely. Because there's something that's really uniquely good about carbon, and maybe, you know, with drinks out in the back of the thing, we can talk about that. But what could well be different is that there could be life forms that have a completely different universe of proteins from the proteins that we happen to use and evolve here. So this is just showing one of these amino acids. This is one that's known as tryptophan. The amino acids are often used not only to build proteins, but to build things like neurotransmitters. So tryptophan is used to build the neurotransmitter serotonin. So there are different flavors of these amino acids, and they have very particular roles. And so the flavors have a chemistry associated with them. So shown here are the two amino acid side chains that are acidic. You've all heard the term, know what an acid is. They literally are exactly that. They donate protons. And there are other amino acid residues that are basic. These like to pick up protons. And these things are colored blue, and this blue to scientists denotes that they have a charge on them. So these basic amino acids are positively charged, and they tend to bind negatively charged things. Any of you who've ever has had surgery and had a heparin lock installed before you went into surgery, heparin is negatively charged, and it binds positive charges on the proteins in your bloodstream that are involved in coagulation. And by virtue of that sticking of positive charges on proteins to negative charges on heparin, it blocks coagulation of blood. So from this small vignette, you get the notion that it's all about stickiness. These side chains give a particular type of sticky character that allows a protein to stick to its intended biological partner, but not to stick to things that it's not supposed to stick to. There are other amino acids, and their names are all given here. I won't go into them individually. And these actually don't like to stick to anything. They just like to stick to water. So you can think of them as being kind of lubricants. They provide a layer of just water-loving stuff on the outside of the protein. There's one other amino acid that has a very special role, and this one is called cysteine. Cysteine, this is an individual amino acid, cysteine. And when these occur in pairs and they end up close to each other, they like to undergo a chemical reaction that's called oxidation. And this oxidation forms a bond between the two cysteines. That bond is extremely strong. So if you try to pull on the two parts that just become bonded together, you can't separate them without nuclear energy or something like that. It would require huge destructive force. You'd have to rip apart the molecule to break this bond. So these things impart rigidity, and you're going to be hearing in Wiley's talk how important cross-linking is in doing architectural things on proteins. Nature's version of cross-linking is shown right here. Any of you who's ever had a perm, in your hair you have these kinds of bonds. And it turns out that there's a special chemical way to reduce them. It smells horrific. And so there's a special way to reverse this by treating it with chemicals that break open these bonds. And then there's another chemical that reforms them. So if you take the hair and you break open these bonds, you can mold it into various kinds of curly shapes. When you reform those bonds, the hair tends to keep its curl. So it's these bonds that allow the reformation of hair in cosmetics. These disulfides are very important for the structural integrity of proteins. This is a protein that binds insulin. It's called the insulin receptor. This is a neat little bomb it's from a scorpion toxin. So it has 1, 2, 3 of these disulfide bonds. And so this actually is made by the scorpion. It binds potassium channels and causes paralysis in whatever has received this dosage of scorpion toxin. Okay, so I've talked about 3 types: negatively charged, positively charged, and just water-loving. I talked about cross-linking amino acid cysteines. But I didn't talk about the amino acids yet that really give proteins their distinctive shape. And it's the set of amino acids that are water-hating. They're called hydrophobic. These amino acids you can think of as being a little oil droplet, having the equivalent of a little oil droplet on their surface. You all know that oil and water separate. So these residues repel water. They force it, say, get off of my surface. And so here's just illustrating that. These are called hydrophobic residues. And when they force the water off of their surface, that allows them to come together and to form a cluster. And it's that clustering of these hydrophobic residues that is really critical for giving proteins their shape. So just shown here are a series of the the hydrophobic amino acids. I won't go into them in any particular detail. There's one last set that I needed to mention, and these I like to call shapeshifters. If you're going to take this beads on a string and allow these hydrophobic residues to coalesce so that you can form a three-dimensional shape, sometimes it's necessary to create kinks in the chain in order to allow the chain to reverse on itself. And the residue proline creates kinks in the chain. Sometimes the chain already is too kinked and you need to make it relaxed, and it's the amino acid glycine that is the most flexible of all amino acid residues on a protein. So that's the cast of characters for the amino acids and their individual roles. Now, when scientists look at proteins, they represent each amino acid by a letter code. Now, some of these are kind of funny because, you know, we have A, B, C, D, we have 26 letters, and not every amino acid corresponds neatly with a letter. So if you have cysteine, it's pretty obvious that it's going to be C, or alanine, it's going to be A. But what do you do with tryptophan? all right, because there's already an amino acid called tyrosine that's taken T. So what do you do? So basically what we've done with tryptophan is we sort of say it funny. We say twiptophan, and we give it a W instead. Life gives you lemons, you make lemonade. So this kind of code, this is the code for the sequence of beads on a string, the 20 amino acids, as you start from one end of the protein right here and move all the way to the other end of the protein right there. And scientists can use this code. This is the distinctive. If you have this code of a protein, you know what it is, and now increasingly we know what its structure is. Now, with respect to structure, all proteins, well, the vast, vast majority defined into fold. In a way, if you think of origami or any other folding exercise, these undergo a specific folding event to give characteristic three-dimensional shapes. So several of these are shown here. You can see that looks very different from that, which looks very different from that. In fact, this protein, you can see, it looks like this lobe here looks a lot like that lobe, which looks a lot like that lobe, which looks a lot like this. This is, in fact, a protein that's assembled 4 units of the same protein into one assembly, and that happens as well. Now, I'm just going to show you a very schematic diagram of how proteins fold. So this would be the chain before a protein folds, and you have these hydrophobic amino or water-hating residues. They cluster on the interior of the protein. They cluster with each other, as shown here. And the residues on the outside are all interacting with water or interacting with other things. For example, if this is a protein that's involved in regulating your genes, it might interact with DNA, and then it would have a surface that is chemically constructed to interact with DNA. And so this is just to illustrate, this is now the outer surface of the protein. Now, I've been showing you the equivalent of saying, oh, let me show you a person, then I show you a skeleton. That's what I've been doing when I've been showing you structures of proteins. I've been showing you the skeleton. And scientists use this skeletal representation just to make things easy. So this is one of these types of skeletal representations. But if you actually fill in all the amino acids, you can see that it becomes much, much more crowded in terms of information content. Even this isn't what, if you were a protein and you came up to look at this protein, it wouldn't look like that. It would look like, it would look like this. You wouldn't see any individual feature of anything. But as you can tell, it's almost impossible for scientists to work with this and get much information from it, because it's really just the outer surface without showing the inner core. It would be like diagnosing a disease in a person if you didn't have X-rays or MRI or whatever. So these other techniques allow us to look into the interior of a protein and understand what's going on inside. And in cases where proteins interact with each other in biology, this one surface of one protein finds a mate in the surface of the other protein. They're matched. For example, one's negatively charged, one's positive, and they come together. Now, for the purpose of cooking, I know you're wondering, when the hell am I going to get back to cooking? Okay, all right, sorry. So for the purpose of cooking, it's important to know that our bodies are at 98.6 degrees temperature. There is no evolutionary driving force for the proteins in our body to be stable at 150 degrees. The evolutionary driving force has been to make proteins stable at the temperature of the organism that has evolved them. And so for that reason, proteins, just as I mentioned, they can fold, they can also unfold. And protein unfolding is extremely interesting and is used by cooks to do all kinds of phenomenal acrobatic feats. So some of the things that can this is called denaturing, when you unfold a protein. So if you shock it with acid or base, for example, you can unfold a protein. If you shear it using mechanical shear forces that tend to pull on the ends of the molecule, you can rip it apart by shear forces. Bubbles create surface tension that when the proteins sit on the edge of this, the surface tension of the bubble can pull a protein apart. Detergents. Remember I mentioned that the inside of a protein has all these hydrophobic residues clustering together. And when you treat a protein with detergent, it insinuates into the interior of the protein and binds all of those hydrophobic things and blows up the protein, basically. And then salts, and maybe most familiar to all of you is heat, using cooking, the temperature of thermal denaturation, thermal unfolding, to cause proteins to lose their fold. So I'm going to show you a couple videos. These are actually these are what are called molecular dynamics simulation. So what these do is they take a model, a computational model of a protein, and they computationally add heat to it. So we can do this. It requires supercomputers and a tremendous amount of computing sophistication. And this is just one basic element, architectural element of a protein that's called an alpha helix. You may know this was first predicted by the Nobel laureate Linus Pauling. And I'm going to show you what happens computationally in the computer when you take this and add heat to it. So there it is. It started as this very regular coiled shape, and now it's gone. And the other important thing is, whereas the coiled shape, what we started with, what we started with has one structure, right? It's a coiled structure. When you go when you heat this up, it goes to many, many different structures. So it goes to a large ensemble of many, many different structures. And what happens when this thing unfolds this way, it exposes all of those hydrophobic residues. And neighboring molecules, there's just shown one here, but neighbors get together and stick and coalesce into an aggregate. And it's for that reason that when you heat up proteins, they unfold and they solidify. They form large, most proteins are about 1/10,000th the size of what can be seen with the naked eye. So it requires many millions, hundreds of thousands to millions of protein molecules to get to something that would actually be visible by your eye. I'll show you another one. So I'll only say one thing about what I do, but what my lab does here at Harvard is we've discovered ways of preventing these small building blocks of proteins from unfolding. And it turns out that when you prevent them from unfolding, they acquire very, very useful pharmaceutical properties. So one of these types of molecules has this brace built into it that prevents it from unraveling. And next year, 2 of these molecules on the left-hand side will be going into testing in cancer patients as a next-generation cancer therapeutic. So if you look on the left, you can see this thing is retaining its coiled structure. If you look on the right, you can see that without the brace, the cyan-colored brace on it, this thing is, waving around between many, many different structures. This is actually on YouTube, so now I'm going to show you how an egg turns white. So this is I'll finish up in a minute, Wiley. Now I've just shown you a little building block of a protein. Now I'm going to blow up an entire protein. So I'm going to take albumin, for human albumin, not chicken egg white albumin, although it's almost identical. And we're going to take this and computationally add heat to it. And what you're going to see, I want you to focus your attention up here in particular. And you're going to see that very early on in this computational simulation, this thing is going to come completely unfolded. So now we're heating up albumin. You can see up here, this is unfolded, dangling off. And if there's another albumin nearby, these guys stick to each other. And then as they start to stick, they build up larger and larger and larger aggregates. And in the frying pan, the egg turns white. So I wanted to mention collagen. Collagen is a structural component of cells. It's used in all cell types to confer rigidity in all tissues. And this can be broken down into gelatin, which is basically a more manageable form, a more soluble form of collagen. It can be used, for example, to make gummy bears, which are a favorite of my children. There are also enzymes that are important, and now we're transitioning to Wiley's talk, because this is the genius of what Wiley's done, is to begin to use these types of enzymes, which are provided by nature, to use them essentially synthetically to make fantastic culinary creations. So this is one which actually just so happens to be a nuisance. It causes browning of food. In the manufacture of cheese, there's an enzyme called rennin, which is extracted from the digestive tract of cows, and it's added to milk in order to chop up the proteins in the milk, and that causes phase separation. So the fat and the protein come together, and the rest of the stuff separates out. So what this does is it chops protein chains, as shown here. And that's what allows you to create curd and whey. And transglutaminase, which you're going to be hearing more about in a moment. Transglutaminase it doesn't chop, first of all, it builds new bonds. It does a cross-linking reaction. And what it does is to take two different amino acid side chains and connect them together. And so that's a cross-linking enzyme that actually forms bonds. And Wiley has used this to deconstruct the protein in shrimp and then rebuild that into a solid matter by using this enzyme to regenerate the architectural structure of a solid protein. So I'm going to end there. I hope there wasn't too much organic chemistry in that talk. And I did want to thank John and Pia for their help in putting this together, and to thank Eric Smith, who's my graphics guru, who helped also to put together a lot of the graphics that I showed you today. So David, should I take questions, or we just move right on? Okay, thank you very much.
Hello, everybody. That was pretty neat. I took a few notes. I'm curious to start cooking with detergent. I thought that was an interesting idea. I think like chicken marinated in Downy or something could be really interesting. So that's my first recipe to try when we get home. I want to first start by saying thank you to everybody for coming out this evening. I want to say thank you to Harvard for having us back again to talk about transglutaminase. You can just pause that for 1 sec if you don't mind. I want to thank Professor Weitz, Professor Vernon. I want to thank John for his help, and everybody else here at Harvard that's been supporting us throughout the year and encouraging us to work with this stuff, to help explain it to us better. I want to thank John McCarthy, who is been my sole R&D guy for the last, I don't know, probably at least a year or so, maybe year and a half, working as an army of one to help us further our work with Miklu. He's about to be leaving us to be opening up a restaurant of his own in the new year, so congratulations to him. I'm happy for him, and his job will be available to any of you out there that are interested. You can talk to him about what that might entail and be like, and if it's worth the effort. But before I talk about Miklu specifically, what I'd like to do is talk a little bit about WD-50 and explain a little bit about the restaurant and how it came about, because I think that sort of segues into our work, our relationship with transglutaminase, or as we like to refer to it, Miklu. But we'll talk about the value of the name in a little bit. WD-50 is my restaurant. We're almost 9 years old. We're located on the Lower East Side of Manhattan, and it was started with a lot of ideas. Obviously, it was a restaurant. We wanted to make food and have you guys in and take your money. But really, one of the things that people don't really think about when they think about opening a restaurant, was something that I wanted to do, was to create a place where I could continue my education as a cook. I went to cooking school. I went to a very good cooking school in New York City. I worked for some great chefs. I sort of did everything that you were supposed to do as a young cook. I followed all the rules. I didn't ask a lot of questions. I just simply did what I was meant to do, and began cooking and learning. And I became very skilled. I knew how to roast a chicken. I knew how to boil a fish. I knew how to poach an egg. I knew how to do all these things. But I didn't. As I got older and I began to be in a position to ask questions, I began to realize that I knew how to do things, but I didn't really know why I was doing them. I might do something 99 times in a row the same way and it would work, and on the 100th time it wouldn't work out. And oftentimes I couldn't figure out where I had erred, what had gone wrong. And so I realized that the typical education of a cook, of a young cook, is sort of, it's not that different in a way from being in the military. It's sort of, well, this is the way we do it. Well, okay, how come this is the way we do it? Because I said so. Or because it's worked that way before, or that's just the way it is. And I think that's useful early on in your career, so that you don't so that progress can occur, so that you can begin to learn things and you don't get bogged down with too much question asking. But as I got older, I wanted to know the answers to these questions. I wanted to understand what was happening while I was cooking. And I realized that I didn't have a complete education. Again, I knew how to cook things, but I didn't know why I was doing them. And so I opened the restaurant as a place where I could continue my culinary education, where I could begin to look for answers to these questions, where I could begin to understand how to cook, understand what was happening to food as I cooked it, as I chopped it, roasted it, boiled it, smashed it, whatever I did to it, understand what was happening to it in order to do it in a better, more informed way. Because it turns out that cooking is certainly some physics, certainly some biology, but it's a lot of chemistry. And this will come as no shock to anyone. The average cook knows very little about chemistry. And I didn't set out to become a chemist, but I set out to sort of understand a little bit more about what was going on. And so that was a primary function of WD-50, was setting up a place where myself and my staff, and ultimately you, the diner, if you wanted to, could continue the culinary education, the culinary journey. And that happens on a number of levels, between what you eat and the environment in which you eat it, the architecture, all sorts of things. But I wanted it to be an ongoing place where we could learn and we could grow, because it turns out that we, particularly as cooks, know very little. And so I had to start to go outside of the traditional areas for answers to my questions. And that is how we began to discover things like Miklu. We realized that we knew nothing, and so we needed to go outside of the traditional formal education of a cook, go out into other disciplines to find out what was going on. Because the answers are out there. They've been out there for some time. They've not been part, again, of the traditional education of a cook. So we wanted to seek out these answers. And in doing so, we opened up this tremendous, awesome, exciting, and terrifying sort of book of information. And in comes these answers to our questions, these explanations that really make cooking interesting. Because again, there's no right or wrong way to cook, but I think there's a more or a less informed way to cook. And that's simply what we're trying to get at WD50, is trying to be a little bit more learned about cooking. We know more today than we did yesterday, and we know more 5 years ago than we did 10 years ago, and about 30 years ago we knew nothing. And so we've only sort of just scratched the surface. We've been cooking for a long, long time, but we've been sort of cooking in the dark. We've been cooking without really knowing how we're doing anything or why we're doing it. And so my hope is that at WD50, through developing relationships with people like Harvard and other people that are experts in other fields outside of cooking, that we can further our knowledge, our understanding of what's happening in food, so that we can make better decisions. Oftentimes, the approach at WD50 comes under scrutiny or under fire, saying that you guys are down there in your lab coats and you're electrocuting the bunnies and stuff, and you're taking a lot of the soul and a lot of the art and the fun out of cooking. And I think it's an easy argument to make, but it's not true, because all we're trying to do is understand what's happening so that we can make decisions. But there's still no right way to electrocute a bunny. There's a lot of different ways you can do it. There's never going to be one right way to cook anything. But there's going to be ways to make decisions along the way. I mean, Professor Verdine talked about poaching an egg, or I think it was poaching, or maybe you didn't specify. You were just talking about the protein bonds uncoiling or denaturing as they get hotter. But there's a lot of different ways to denature those proteins. There's a lot of different ways to poach an egg. There's no right or no wrong way. You might like your egg poached at 64 degrees for 45 minutes, and you might like your egg poached at 70 degrees for 30 minutes. And neither one is right or wrong, but it's just a matter of understanding how those variables will affect the end product so that you can make it the way you want. And I think that's really what we're about, is trying to understand these ingredients so that we can make better decisions, because I think learning is pretty cool, and I think whoever knows the most when they die wins. And so we're trying to win. But the nice thing is, too, is that we'll never get there. We'll never know everything. And so, if we can get this ball rolling and begin this process, or somehow be part of the process, that other people can pick up and continue, that's really my hope. My wish is that when people come to the restaurant and come and work for WD50, and when they leave, they say, I know more now than I did before. And that makes me feel like it's a success. And so to that end, we come across meat glue, transglutaminase. Well, what is meat glue? Meat glue is a pretty cool name, I think. I mean, it's called transglutaminase. It's an enzyme, but meat glue certainly sounds a lot better and a lot cooler and a lot more evil. And I like the sound of it, but it also is more useful ultimately to help inform your thinking about the product, because when you think, okay, here I have a bunch of transglutaminase, what can I do with it? That's not helping you sort of wonder what to do with it. But when you say, I have some meat glue, what can I do with it? You can start to think, well, is he serious? Does he mean meat glue? And I mean, yes, you can glue meat together. You can glue most land-based, well, not land-based, most meat, fish, poultry, seafood, all have enough of the requisite amino acids, which are lysine and glutamine. Those two things need to be present for this covalent bond to happen, and most things have them in them. Not everything, but most meats, fishes, poultries have them in there, and that is pretty fun. But it also gets your brain going, like, okay, what can I glue? What can we do here? I mean, again, Professor Verdine talked about these bonds like to stick to things that are their biological partners, and I like to try to stick things together that aren't biological partners. I think that's, in a way, kind of fun and more interesting. But meat glue was originally designed by people who, not designed, it was discovered by the good people at Ajinomoto, and in some of its early applications were to just take scrap meat and use it. When you have a piece of fish and you get nice portions from the head all the way down towards the tail, but as you get towards the tail, it sort of tapers. And what do you do with those flat pieces? Well, if you get 2 or 3 of those flat pieces and you take meat glue, suddenly you can stack them together, glue them together, wait for this bond to happen. It does take some time. It's not magic. It doesn't happen instantly, although there are certain ways that we've discovered that you can accelerate it. And then you have something that we'll show later. For instance, this is 10 pieces of meat glued together, and that's pretty neat. And It also is allowing us to cook things in ways that are a little bit easier. You know, as things change and taper, it's hard to cook them uniformly. I think we've all had a piece of meat or fish or chicken that's not cooked the same end to end. And as a chef, that's maddening, because we really want you to have a properly cooked everything end to end, and we hate to see that. We hate to know that towards the tail it's going to be overcooked than towards the head. And these are why meat glue is helpful, is because we can sort of create uniform portions that we can cook more evenly, more effectively. And again, we can improve our craft of cooking. It's not that I'm trying to make a jackalope. You know, I'm trying to, although that would be kind of interesting. I'm trying to cook things in a more even way. I mean, again, I'm not criticizing God. The animal didn't grow incorrectly, but it's an animal. It has different parts, and it's hard to cook. It's, you know, it's hard to cook a shoulder of a cow or of a pig evenly, which is why it's either usually cooked for a really long time so that everything can break down, all the connective tissue regardless of size, or you take it and you reshape it and you can cook it evenly. And that's sort of where the fascination, where the interest with meat glue is. And this is our very first application of meat glue. This was you can press play again, please. This was the very first thing we did. We were introduced to meat glue about in late 2003, early 2004 by Heston Blumenthal and his team at the Fat Duck outside of London, a great chef and a great restaurant and a brilliant man. You should bring him here, by the way. You tried. Okay, well, never mind then. Sorry, you're stuck with me. But he was the one, and his team, that turned me on to this product, and this was the very first application that we ever did with that. I worked for Jean-Georges Vongerichten for many years, a great chef, who taught me how to make a sausage out of rabbit. We used to take this is rabbit, some chicken meat, some parsley, and the livers of the rabbit, and we used to take it and bind it with some egg yolk, mix it together, and we'd wrap it in little tubes of plastic and then in foil and poach it again, so it was a uniform shape. This is why sausages are so popular, because they cook evenly. And then we would slice it. And sometimes it would crumble, sometimes it wouldn't cut cleanly, sometimes it would fray. And when I got my hands on some meat glue, I said, aha, this is what I'm going to do. I'm going to improve on this dish. I'm going to make a casingless sausage. And that's exactly what we did. We took, I think, 1% of the weight of all the sausage mixture, added some glue to it, twisted it up, let it do its thing, poached it, and sliced it. And you can see it's very, very clean. And thus our relationship with meat glue was born. And it's an ongoing love affair that has taken the restaurant to some great places. And we're going to show you some recipes up there. We've been talking about shrimp noodles for the last half an hour, and I made a sort of last-minute decision not to show the video on shrimp noodles, which I guess was a mistake. But I'm going to show you a number of dishes that we've done at the restaurant where we've worked with meat glue. You'll see how it's handled, hands-on, and you'll also see the finished product, which I think is very useful. And then we're going to go on to some sort of 2.0, 3.0 applications of meat glue, and then hopefully, if any of you are still awake, we can maybe have some questions. Can we go a little bit forward to can we go to what is it, 10? Can we go to 10? Excellent. We're going to show you a steak dish that is actually at present not on the menu, but was on the menu up until very recently. There are other versions of other types of steak that are on the menu right now at the restaurant, and we're going to show you this one, which is it's a flap steak, which is a piece from the diaphragm of the animal. We're going to show you how we take that sort of flat piece of meat, which is normally very difficult to make a video of. I'm just kidding. Is difficult to work with because it's flat, and you can't you can't get a piece of meat that's that flat. Oftentimes it's used for things like fajitas or other things. It's cut very thinly and sliced and seared. But we're going to take it. Yeah, that's perfect. Just leave it there if you want, or maybe just go forward. Those are shrimp noodles, by the way. We're not going to talk about that. Moving on. This is a Wagyu flap steak, like I said. And the first step to gluing this steak together is to get the enzyme in solution. And it is water soluble. In this case, there are different types of the enzyme. There are about 5 different kinds that the manufacturer has, depending on your application. Some are only sprinkle coated on. Some are mixed into slurries. Some are specifically for yogurt. Some have higher concentrations of the enzyme. It depends on your application. They've really refined the different types, which is very interesting. In this case, we're using what's called GS, and this is a mixture of the enzyme, a little bit of maltodextrin, sort of to keep it free-flowing in the package. It's a type of sugar. Some phosphate salts, which raise the pH of the enzyme. I mean of the solution, I'm sorry, not the enzyme. They raise the pH of the solution so that when it's blended with water, it doesn't begin to set. It will stay fluid for a really long time. If you take a different type of them, you mix it with water, you have to work with it very quickly before it becomes kind of like a gluey, muddy, sticky mess. In this case, because of the presence of the phosphates, the pH is high enough that the enzyme is actually inactive until it touches the substrate of the meat, lowers the pH, becomes active. Here what Tom is doing, and you'll have to forgive the very high-end green painter's tape on the lower left-hand side of the machine. You'll see that later on we had the presence of mind to remove it. I apologize. But in this case, what we're doing, we had to really blend it or shear it very, very aggressively to get it into the solution, and there's a lot of bubbles. And we learned the hard way that just taking it as it is with what appear to be very tiny bubbles causes a problem, because that's actually air, and it gets in between the bond, and the bonds are not as strong, and the meat is prone to sort of peeling apart, and that's kind of gross. If I sent you a steak that was kind of talking to you and wagging its tail, and that's not so nice. So what we do here is, you can see we've used the vacuum machine to just pull the air out, and you get this sort of almost caramel-colored liquid. And then here is the Wagyu flap steak. Again, this is from the diaphragm of a cow. And conveniently, if you're to go to Wikipedia and look up meat glue, there is a picture of a flap steak. I didn't know that until just recently, but that's a nice coincidence. But here, Tom is taking the flap steak, which he's cut. We've removed a lot of the silver skin or connective tissue, as we were discussing earlier, because we're not going to cook this at a long enough temperature or time temperature sort of graph to convert that collagen into gelatin and make it friendly in the mouth or edible. So we want to remove most of it, so we just have pretty much the meat here. And he's brushing it with the enzyme, and he's putting the two halves together, and then you're going to see he's going to wrap it up, apply a little bit of pressure, and again, it's a function of time for this reaction, for this bond to form. There are ways to speed it up. If we had thought to show you the video of the shrimp, you would see that we cook the shrimp at a specific temperature, because it's the temperature at which the enzyme is most active, and you get a little bit of heat setting from the temperature, and it helps the process speed up a bit. If only Tom really worked that fast. But you see there what he's done is he's taken it, applied the glue, and wrapped it up, and we've let it sit overnight. Again, overnight is ideal. 4 to 6 hours is probably the minimum, although we had a rather unplanned experiment in the middle of service the other night where we were able to get satisfactory results in 30 minutes. But that's not the kind of working conditions we seek out. It was a little bit stressful for all involved. Well, let's not talk about it. You can see, again, to the untrained eye, there isn't much of a seam. There is certainly a seam you can see. I mean, it's a giant close-up of it, but to the untrained eye, I don't think that you can see that seam quite so much, and again, that's nice. We try to line it up in such a way that the grains are all running the same way. And again, ultimately, what this allows us to do is to take a piece of meat that was difficult to get nice and red and medium rare or medium even, and look nice. And in this case, we're able to see right there. You can't really see the seam at all, and I think that that's fantastic. And that's simply a steak that's been roasted the old-fashioned way. There's not a lot of sort of high-tech cookery after the fact. We just roast it the old-fashioned way, and you get a real nice round eye of flank steak and flap steak. I'm sorry, we also do it with flank steak. But I think that that's neat because we created a cut of meat that didn't exist before, and we made that cut of meat much easier to cook, much easier to serve. We made an improvement, I think, on something. I don't want to sound like, nature's not wrong. It's just sometimes not convenient, and we made it a little bit more convenient and a little bit more practical and at the end of the day, that's what restaurants are all about. It saves us money, it saves us time. It makes cooking, the preparing of your meal a lot easier. And there was actually a lot of meat glue on that dish. The garnish, which is right here, you'll see is barley. What was interesting is that, again, there's lots of things, meats, fishes, and poultries, shellfishes that have a lot of, or a sufficient, adequate amount of lysine and glutamine present in them to form this bond. But we started thinking, well, what about things that don't have enough of those things? Can we introduce them and get a bond? Can we make a bond where there wouldn't normally be one? And we looked around and we discovered, we found out that gelatin, which is rich, I think mostly in glutamic glutamine. I think it's high in glutamine. It might have some lysine as well. It probably does, but I shouldn't really be saying any of these things. Professor Verdine is shaking his head. No, don't say that. So we realized that meat glue and gelatin are unbelievable friends. They love each other. They make a fantastic bond. Gelatin and the enzyme are great together. So we started thinking, well, what could we do with that? And the first thing we did was we took soybeans, pureed them, and then separately we took some gelatin and some of the enzyme, which you can see here. Tom has taken some gelatin, he's dissolving it in water, and separately he's going to dissolve some of the enzyme in the water. And that's exactly what we did. And then we combined that with pureed soybeans. We spread it very thinly, allowed the reaction to take place, and it wasn't vegetarian, mind you, but we had ostensibly a noodle, a sheet of pasta made from fresh soybean. The idea was to play off, I don't know, for those of you that know what yuba is, you heat milk up, soy milk up, and pardon me, in a skin forms, and you pick it up and you let it dry slightly, and it's very, very interesting texture, but it's made from dried beans, and we sort of wanted to make a fresh soybean sheet, and that's what we did. And then rather than pureeing something with the meat glue, we thought, could we bind something in it? So we took quinoa the first time, and we just cooked some quinoa and mixed it in that slurry of gelatin and meat glue, spread it very thinly, and we put it in the fryer, thinking that all hell would break loose. And it turns out that when you say that those bonds are strong, no kidding, they're really strong. I mean, the fryer is a nasty place. And we dropped sort of irregularly shaped pieces of this grain bound with the enzyme into the fryer, and they got crispy. And it was like this aha moment, like, oh my God, really? This isn't supposed to happen. And we thought that it was going to be, hospital burns and that sort of thing. And it turned out to be a huge success. So in this case, we've taken a similar approach. We've taken barley, we've cooked the barley, we've mixed it with some caramelized malt powder that's typical in beer making. College students know a lot about that. And we've mixed the enzyme and the gelatin into that solution, bound the barley with it, and we're going to pour it out, allow it to set over time, and then you're going to see that what happens once it's cool. And you'll have to forgive, Clay likes to write notes on his hand. You'll see he's got a note on his left hand there. I'm sorry about that. What happens is that you'll see that you've got this great, beautiful cake from barley, and it's we can put it in the oven, we can heat it, we can deep fry, and you're going to see what he's doing. He's going to break it into little pieces, and it has this beautiful sort of knobby look to it. And then just imagine that he puts it on that tray to the left, and we put it in the oven for 5 or 6 minutes, and then you're going to see him hit it with the blowtorch, which is exactly what we wanted, because we wanted some of those those caramelized Maillard reaction flavors, because that's a nice complement to the beef, we think. And again, beef and barley and malt, it's all pretty tasty combination. But it was really kind of unbelievable to us that we could get how strong this bond was and the things that we could do with it. And the fact that it held together. And now, again, it's not vegetarian, and I'm sorry for those of you out there that are thinking that there's all sorts of wonderful vegetarian things that are going to come of this, but there's gelatin in there, and there's no good substitute that we're aware of yet. I mean, it's an interesting project to talk about. But look at that. I mean, there's not even any synuresis. There's not any weeping. There's no liquid coming out of there. It's really amazing. And again, Professor Verdine talked about how strong these bonds are. I mean, he mentioned nuclear energy, and we don't have one of those in the restaurant. But so there is what we think kind of almost a 2.0 application of meat glue, putting it in a place where it doesn't belong. Not that gluing chicken skin to a salmon belongs, but really putting it where it doesn't belong in a way that is creating something not novel or goofy, but actually something delicious and something that when you take a second and think about it makes good sense. So here is a dish with codfish served in a broth with a puree made of coconut milk and freeze-dried peas, and a broth made from carrot-flavored dashi, and a pasta that is got nori seaweed rolled into it. It's a very Japanese-sounding dish that no Japanese person would ever endorse in any way at all. But it starts with Roxanne, who, unlike Clay, doesn't write her notes on her hand, she tattoos them. You can see in a moment. Roxanne takes basically 2 cod fillets, strips them down, and lines them up. You can see, again, she's using the same solution, the same slurry that Tom made earlier in the day, and it's still very liquid, very fluid because of those phosphate salts in there, keeping the pH rather high. And she's gonna brush. This is an entire fish, 2 sides of codfish, and she's gonna brush it fairly liberally with this solution and roll it up. And again, what's really nice is we've got all the grain of the meat running the same direction, so it comes time to slice it. We're cutting through the grain, which is going to make for a better mouthfeel for you guys. When you cut through the flesh of an animal, it helps make it easier to chew, which is nice. And it's also going to give us a very uniform shape. For portions, there's no waste here. I mean, again, you saw that fish, it tapers quite a bit towards the tail. Codfish have gigantic heads, and the flesh around their collars and necks is very thick. And now we're able to sort of equalize that and get a shape that allows us to utilize the entire piece of fish and to cook it in a way that's very uniform. For all involved, it's sort of a win-win situation. And you'll see here she's just laying them all out, and it's actually a lot of fish, but she's going to manipulate it in such a way, give that bond time to take place, and you're going to get a really nice, beautiful fillet. It's not dissimilar from the meat. In this case, the meat was like this, and these are sort of lined together and stripped up. But it's a very similar situation, and I think, again, there's nothing wrong with fish in the way a fish grows, and obviously it needs the bones and everything to swim. But when you take it all out, and roll it up in a lot of plastic wrap, you get a really nice portion of fish, which you'll see in just 1 second. So again, that's an entire codfish that's been allowed to. There she's just piercing it to get the air pockets. Obviously, there's bound to be a little bit of air between as we're pressing it. We're not using a machine. There's the human factor here. So she's just trying to do the best she can to remove all the air, so that when we cut into it, that there are no air pockets, and you can see that it's fairly successful. And again, I think this is a pretty exciting thing for the average cook to think about, like when you can start. These are very basic applications, the steak and the fish, and sort of what people had in mind when they brought meat glue to us. And the barley is a bit more of an advanced application, and I think we have a couple other fun ones here, and you're going to see another vegetable application in a minute. But really, that's an effective use of it. I mean, I don't want to say perfect because that would go to Roxanne's head, but it's pretty well done. And again, it allows us to sear that piece of meat or poach it or whatever in a very controlled and now uniform way. So we can screw it up evenly. And again, this is served with a dish of a puree made from carrots and coconut, and some carrots that are sautéed in a little bit of sugar and butter and fish sauce, and then the pasta is topped on it, and it's made with a broth. Again, you get some better shots of it. I mean, anyone that knows what a cod, you know, if I were to show that to you, if that was in the deli counter, you would know that that's not the way that cod grows. And you might now speculate, wow, I wonder if they're using meat glue to create that, and it'd be a safe bet. And so there's you know, our codfish dish. And the last thing I'd like to show you, the last video I'd like to show you is our one on radish sheets. And again, this is taking. Last year we had made some things, some apples. I believe was it pears and apples, or excuse me, pears and green apples that we had. Again, started thinking, how could we glue things together that don't have the necessary constituents for that to happen? And we messing around with carrots and celery, apples and pears, sort of old friends, but none of them, to my knowledge, have enough lysine or glutamine or any lysine or glutamine in them for the meat glue to find a way to make a reaction. But we started to think right before we were here, we just brought some sort of testers, that if we impregnated the fruit with the gelatin, that maybe we could dust the enzyme on the surface and apply a lot of pressure and get a bond to take place, and hopefully grab the two things and not simply just be a bond that existed between them, and then they would then peel apart. And that was some of our early problems, was that it wouldn't that it would form a beautiful bond, but the two things wouldn't hold on to each other. They would just be on either side of this gel. But we've been working on it a bit, and here we have radishes that are again, they don't have any gelatin in them, so we're going to put the gelatin in them, and then we're going to take a little bit of RM, which is sort of the workhorse of the transglutaminase family, and a little bit of TI, which is their extra strength version, in equal parts, and really just dust the surface of the radishes with the enzyme, and then get a bond that takes place. Because the gelatin, we're going to use the vacuum machine to actually impregnate ostensibly the radishes. We're gonna impregnate the radishes with gelatin. We're going to put gelatin in the radish where it didn't belong, so that we can get that reaction. And so Brian is going to, you know, there's a lot of space, there's a lot of air in your average radish, and we're going to fill that space with a little bit of this water that's rich in gelatin. It's so much cooler the other part, but everyone gets excited when it does that. But the gelatin is so there you have radishes that are sort of drunk on gelatin, and Brian's going to drain off the excess and add a little bit of the enzyme, and then he's going to lay it out and apply some pressure, and you'll see that the radish sheet will be effective. This was Brian's very first time doing this just the other day. He's a brand new employee, so he forgot to mix those two containers. They're actually supposed to be mixed. It's equal parts of the two items, but he forgot to do that. He was excited, and we just sort of went with it. Like I said, he's brand new, and he's a great guy. But what he's doing, he's adding a little bit of the enzyme to the mixture. He's going to lay it out on plastic wrap and put a little bit more on top. And you know, you use the word sticky, and then we're using the sticky nature of these bonds to what I believe to be great effect. So here he's just taking a little bit of plastic wrap, and he's going to lay them out in a single layer, very thinly sliced radishes, and you know, again we're able to play up the sort of thermal irreversibility of these bonds and heat these sheets of radish, which is great because we don't saute it, although we could, but we just kind of warm it up, and he's a superhero, as you can see. We just heat these radish sheets up in enough so that they still retain a little bit of that crunch from a raw vegetable, but they get warm. And if you did this with just gelatin, let's say, they would just sort of slide apart. But because we've infused the gelatin into the radish and then put a little bit of the two types of meat glue on top, we're able to get that bond. And what Brian forgot to do is he's supposed to take a dry brush afterwards and brush off all the excess, but he was very enthusiastic. And this is why we bought so much meat glue this week, because so normally I assure you it's not quite so aggressive in the meat glue department, but that is then pressed overnight and allowed to sit so the reaction can take place. We try to put a minimum of say 10 pounds on that so that it can really, you can sort of force the issue, for lack of a better word, and then when it's done the next day, you're left with this, which is pretty neat, and pretty durable, and that you can do a lot with that. So that's pretty neat. It's just about like where can your head go with it, and there you can see we've cut it up thinly, and so those are some of our work with meat glue, with sort of our most recent effort here from Chef Brian, and again I've brought some of it so you guys can see. It's pretty neat. I'll come over here and you can see these were made yesterday, and you know it's pretty cool. It's pretty strong. I don't know that we want to pass around a radish. It's going to get weird somewhere up in there. But you know, you can really start to think about some, I don't want to say sky's the limit because we still are working with this sort of thing, but you can really get some interesting ideas about what's possible. And you know, you're going to have to trust me when I tell you that this can get hot, because it really can. And I think that's ultimately what's interesting about this is being able to use it sort of in the it's a 1.0 version, which is you want to put the slideshow on. That's it for radish sheets. I've got about a dozen images that are dishes over the years at the restaurant that all have meat glue in some way, shape, or form, that we're just going to sort of put up there as a loop to hopefully distract you from me. So again, this is something that we're pretty proud of and pretty excited by. I think it's pretty neat in how it works, and again, what's possible. And to that end, we have some other items here. This is tofu, which is very high in the necessary sort of protein and enzymes for meat glue. Meat glue is very happy with tofu, but when you blend tofu, obviously it's a protein gel, and when you blend it, it can't re-gel. There are not too many things that have that property. There are a couple of things I know of, but not too many. Tofu's not one of them. So when you blend it, it's done. But if you reintroduce some meat glue into it, you can reset it. So that opens up a lot of possibilities as to what you can do with it. And this is something that we no longer serve on the menu, but it's something that I really like. This is Campari tofu. We've taken tofu and we've taken some alcohol. Campari is a delicious liqueur. We've reduced it down and added it to the tofu, and we've got tofu again. And you can control whether you want soft tofu, firm tofu, and that's, I think, pretty interesting. And again, just sort of makes you think. Again, apologies to the vegetarians because I know you like your tofu, but sorry. This is delicious and pretty neat, and it's a great flavor. There's lots of directions you can go with that. We served that, I think, with eel. That's right, with smoked eel. That's a chicken right there. That's a cold fried chicken, and it's all leg meat that we've set with the glue into a tureen, and then we've cooked it, and then we just bread it and fry it briefly and let it get cold, and we serve cold fried chicken with a little bit of buttermilk ricotta and caviar, sort of the high and the low. It's having fun with leftovers. In that case, you guys, I know, are all having caviar on your fried chicken, I'm sure. But that's a good one. Here is another example of taking something that doesn't have enough. Nuts are high in protein, but I don't think the right kind of protein. So we got excited that nuts might have something to offer. So we started blending nuts with the enzyme, and nothing happened. And so then again, we brought the idea of the gelatin and the enzyme combination together, and here we've made ostensibly sheets of peanut butter, which is fantastic. And then we take the peanut butter sheets and we just cut them into noodles, and we serve that with beef, sort of a fun riff on pad thai, like beef and peanuts. Again, these can be hot, which is pretty neat. You can saute them, and we make a peanut sauce, et cetera, and that's another fun application. I'm sorry, I meant to put them on the plates, but the black is kind of sexy, so I'm going with it. And this is the last guy I'd like to show you guys, and then hopefully we can all go out for drinks together. This is a skirt steak, a lamb skirt steak, and you talking to me? Oh. Lamb skirt steak's really very thin, very thin, and we called our butcher up and said we wanted lamb skirt steak, and he said, okay, but nobody buys that from me. You're the only person that buys it from me. What are you going to do with it? And you know, I told him that I was going to stack it up 10 high and glue it together, and he got really excited and sent me a bunch of it, and that's really what we've done here. You're gonna have to get nice and close on this one. This is you can or cannot. This is 10 high lamb skirt steak that has been mixed with GS and then pressed together over time, and that, I mean, again, there'd be no way to get a piece of lamb skirt steak. This cut of meat does not exist anywhere that I know of, except for at Harvard University. And again, I think that this is a lot of fun, and it opens up the possibilities of what you can do with it. Like, again, lamb skirt steak probably mostly goes into, again, things like fajitas or ground meats, things where it's too thin to be practical. And then here we have what I think is a really fun, nice use of the meat glue. Those are sheets of oh no, I'm sorry, I'm looking at the TV. And those are sheets of shrimp. We made cannelloni. We blended the shrimp and spread it out, made cannelloni. That's skate fish. Skate is a very irregular shape, and we're able to make sort of blocks of skate. We call it a skate cake. We have all sorts of weird terms for the food we make, but we cut it into blocks and sear it and saute it in a way that's very practical, and again, uniform. So that's all I got, guys. I want to say thank you again to everybody. I'd certainly, if we have time, love to encourage a dialogue of some kind.
We'll take questions for both Ray and Wiley.
Yes, indeed. Does meat glue have a taste? Well, no, it does not have a taste. Although it's interesting that the professor said that a lot of these bonds have a lot of flavor. These proteins have a lot of flavor. Meat glue does not have any perceivable flavor. If anything, overuse or misuse of it can end up in textural perceptions, but I don't think that you will ever be able to taste meat glue in something. You may notice that something doesn't feel the right texture. For instance, we've used it on very thin things like sardines. And we used to take sardines and shingle them together so you could get sort of like a shingle of sardine. And we realized the next day that it wasn't that you could taste the meat glue, but the sardine had taken on a texture because the bond had passed all the way through. It wasn't still on the surface. It passed all the way through, and so it had given the sardine a texture that was not, it wasn't necessarily unpleasant, but it didn't feel like a sardine normally feels. And sometimes they use that people use that aspect of meat glue to their advantage. Sometimes it's part of the snap in a hot dog. It's there on purpose. But no, I'm getting off topic. I'm sorry. No, it doesn't have a perceivable flavor.
Yes, I was wondering, you probably, compared to people in the food industry, order fairly small amounts of this stuff. Do you find interest from your suppliers like Ajinomoto in collaboration on finding new applications for this? Because, in the meat industry, people who are using this to make hot dogs or chicken nuggets or whatnot will be ordering it by the, say, 55-gallon drum or 2,000-pound tote, and you guys are probably ordering small lab samples and so forth. Are they interested in collaborating with you?
They've been very supportive with us over the years. Yes, I mean you're right. We don't represent a very large market share, but we do. They are interested, I think, in creative applications, and there are a lot of creative applications for meat glue, from field dressings for the military to chocolate to cheese making to all sorts of really cool things that I didn't even come close to thinking of. But we get great technical support from them. They've been very helpful with us and very, very supportive. And I think that the chefs represent a small niche market, but certainly a prestigious market in a way. Yes.
Well, thank you very much. I think if Dr. Frankenstein was here, he would be very excited. No, but have you considered using any of the vegetable or gelatins that are derived from seaweed or something? Would those be possible? Have you tried them?
There would be no way that I know of to use an agar or a carrageenan or a gelan, to name a few, to get the same results. All of those things melt at a much lower temperature, for sure. They don't have the same flexibility. They don't behave the same. We do a lot of really neat stuff with all of those ingredients that I just mentioned. But I don't think, I'm not saying it can't be done, but I've not been able to achieve a heat-stable noodle using like a polysaccharide or something like that. I've not been able to do that.
Yeah, it seemed like you were using a lot of plastic for a small amount of food. I was just wondering if you're looking at more environmentally friendly ways of doing that. No, sir. But like fixturing, that type of thing, where you could bring it into the home or bring it into a commercial situation?
Well, we're always looking for ways to be a little bit more responsible as individuals. I think the use of meat glue is in and of itself a way of being more responsible and putting less things in the trash. It's probably, I'm not going to defend anybody, but it's a fine line between making sure that you don't get in trouble for that, there being air pockets in the glue, and me not going too crazy over how many rolls of plastic wrap we have to buy each week. But yes, we're always interested in ways that we can be more responsible for the environment. We can be more cost effective. Yes, I mean, that's a lot of, for what it's worth, that's a lot of orders of codfish. That's not like 2 cod that she wrapped up like a mummy. So I hope that we're doing the best we can to balance that out.
I was just wondering if you could describe the procedure you make the peanut noodles with. Is it similar to the barley or?
It's yes, the peanut noodles. We melt down some peanut butter, some peanut oil, and then we introduce. You need a little bit of water in there, and so we get some water in there with the gelatin, and the TI and the RM. We use two types of meat glue in that particular application. We put it together in a food processor, and we just puree. Is it a food processor or a blender? We put it in a blender. A food processor, yeah. We just sort of puree it until it's nice and smooth, and then pour it out between two sheets of plastic, only two sheets of plastic, and then we roll it very thinly and let it sit over time. And you know, it does have a little bit of sort of the fine specks in there, but I like that. It does add a little bit of that natural organic nature to it. I don't want it to look exclusively like it came out of a vending machine. I want it to look a little bit like there's a human touch.
Very impressive. How long did it take for the codfish ulad to bind together?
I'm sorry, how long?
It took for the codfish.
Again, if you could wait overnight, I think that would be ideal, and I would say you'd be almost guaranteed to have success, but we've, under extreme circumstances, 4 to 6 hours is probably as far as I would go. Like I said, we accidentally had an experiment over the weekend that was under half an hour, but nobody enjoyed the process. It was not, you know, in the lab under controlled conditions. It was under extreme duress. But I'd say, you know, overnight, and you'll be in good shape.
Is this something we can make at home? And if not, do you have any thoughts on how to make it more accessible for home cooking purposes?
Can they make meat glue at home?
Can we buy meat glue?
If you can buy the enzyme, sure.
Well, you mean can you get the enzyme?
Yeah.
Like,
Can you buy meat glue?
yeah, and like which
Put
tools
it
do we
into
need?
Amazon search engine, meat glue. It comes right up. Go figure. But you can buy meat glue from Amazon.
Okay.
You should store it in the freezer because it is alive and it likes to be cold when it's not being used. So I would keep it in your freezer in some sort of a Ziploc or something like that. It comes in a powdered form. But yes, you can get it and you can experiment with it. Absolutely. I would recommend maybe, you know, it would be helpful to have a scale so that you can think about concentration levels, percentages. You very rarely need more than 3/4 to 1% by weight in a mass.
Hi. I was wondering what your most epic fail was for trying out meat glue.
I'm not telling that.
All right, your second most epic fail.
You know, I mean, that's part of the beauty and part of the frustration with it. There are people in the restaurant who are better at working with. This is great. We lost 2 of them over the weekend because they didn't stick together, and that led to our 30-minute, you know, experimentation. And there are variables that even we don't understand. Some people in the restaurant speculate that the temperature of the meat has something to do with how well the reaction is. I don't know about that, and I can't. That would be more a matter for the professor to talk about. But you know, I could come up here all day and tell you about my epic failures. That's not something that I'm short on. But you know, again, we trying to glue things that didn't necessarily taste good together, combinations that didn't work, not thinking the whole thing through. You know, I can glue a duck to a lobster, no problem. And even if you thought it tasted good, texturally it might be weird because, again, there are muscles and they contract, and they don't contract the same way at the same temperature. So there's lots of things to consider, and sometimes an idea sounds good. Peanut butter noodles was really neat, but then, you know, the medieval beast was not. And so there are lots of things that this you know, this is fun. This is steak tartare, and we just put enough meat glue in the tartare for it to hold itself together, but so that when you ate it, it didn't feel like it was bound up meat, that it doesn't crumble. But how is it that you're able to balance it upside down on itself when steak tartare can't really be formed? There are times when people get the ratios wrong, and it does taste kind of bouncy, a little bit weird. The sardines, as we talked about, I don't think that was a successful application. We ultimately discontinued that almost right away. It's a pretty neat product and it's a pretty fun product, but it's not magic, you know. And again, we want to make food that tastes delicious. That's our sort of our end game. And along the way, we do have some dogs that have happened, you know.
Very cool. On the lines of combining different types of meats together, have there been any successful, you would say, combinations of different types of meats you guys have glued together? And then just a random question, is meat glue healthy or unhealthy, or does it really matter?
Well, I think it's probably better for the professor to talk about the health aspects of it. I mean, have there been great combinations? Is that what you're asking? Yeah, I mean, putting like crispy chicken skin is kind of a universal favorite. People love crispy chicken, and it's nice when you put it on a piece of shrimp, or you imagine fish skin is also really nice. And we've had some fun sort of swapping the things. I think that fish skin on chicken is delicious, but I didn't serve it to anyone because I thought it would be a stretch. You know, and it reminds me to your question about epic failures. Oysters were an epic failure. I wanted to make a terrine of oysters because I don't like oysters the way they are. And so I wanted to change the shape because that's the only way I can eat an oyster is if I change the shape. I don't like the texture of them. And I've not been able to get that to work. And I think that would be an interesting idea if there was a way to more effectively predict what would and wouldn't actually bond. And I'm sure that there is, but that's not a question for me. Too much salt?
Yeah.
Is that what it is?
Maybe,
Yeah.
yeah.
For us, it had to be the water. Yeah. We thought it was just too wet that they would slide apart. But would you like to speak to the health aspects of it? I mean, I know a little bit about it, but
it's a naturally occurring protein. It would be equivalent to eating whatever is actually making glutaminase. So it gets into your stomach, it gets broken down into amino acids and is food.
Yeah, I mean, your intestines, I think, kind of have at it pretty aggressively and break it down in a way that it doesn't stand a chance.
Yeah.
Some reviewers say it's banned in Europe? It's not banned in Europe. That's not true. It's not banned in Europe. There are some people that have put forth the notion that there's a way that adding meat glue to things that have gluten in them and people that can have a gluten allergy can have small amounts of gluten. It's not that they can have zero; they can have small amounts. I believe even a celiac can have very low levels. But there are some people that say that meat glue can react with gluten to increase the level, the allergen in the gluten. But there seem to be some conflicting stories on that. And I don't think that the celiacs are avid test group candidates for that sort of thing.
Are there any food safety concerns with the potential bacteria on the outside of something like the steak you were using, that you're putting that in the middle and then you're only cooking it to medium rare?
There are, and that's why I think it's about having responsible processes along the way, about handling the meat responsibly. You saw those people were wearing gloves. It's about, yes, like anything. I mean, they're the same way it's dangerous to have somebody handle raw fish when they're making sushi and then hand it to you to eat. But yes, you are introducing bacteria potentially on the inside where it might not get to the right temperature. That is an issue, and that is something we try to be aware of. And I believe that if we practice responsible hygiene along the way, that we can greatly reduce those risks. There are a lot of risks, obviously, that one assumes when going out to eat, and certainly I think that you raise a good point, and we try to be responsible about it. I'm afraid to say this, knock on wood, we have had, to the best of our knowledge, no issues with that particular product, or as a result of using meat glue, and like you said, sort of turning the bacteria on the inside out.
So tofu is derived generally from soy milk. I was wondering if you have tried infusing soy milk into your vegetables in order to create vegetable sheets. And as a more silly question, can you actually glue your hands together with?
It's not a silly question. I mean, I think it would be awesome if you passed out at a party and woke up like that. I think that would be That would be so cool, but unfortunately, it does not. It does not work that way, you know. Or I might be walking around like this. But we have tried putting soy flour, soybeans in things in the hopes of getting a reaction. Not it's not been we've not been able to get a bond that's strong enough, which is why we've had to sort of augment that with gelatin. Even a fresh soybean on its own didn't, with just the enzyme did not. I mean, I would love for that to happen because I would love for there to be a vegetarian alternative. I mean, when I first found out, oh, it works with lysine and glutamine, I went right down to the vitamin shop and I bought a bottle of powdered lysine, a bottle of powdered glutamine, and I thought, I'm a genius because I'm going to make vegetarian noodles, and you know, some Swanson or somebody's going to call me, and I'm going to be a billionaire. And of course, it's not that simple. And otherwise, Ajinomoto would have done it, or somebody else would have done it a long time ago. There's just not. You can't. Again, I'm not sure why you can't introduce lysine and glutamine in a powdered form and get. And that's sort of above my pay grade. I'm sorry.
You don't have to go too far into the process, but where does the enzyme come from? Say, how is it harvested?
It comes from bacteria. Yeah. I know it's from a bacteria. I mean, originally it was, I think, bovine when it was discovered, but it's harvested from bacteria at this point.
Yeah.
I mean, it's somewhat proprietary, right? But it's harvested from bacteria.
Yeah, I guess it's originally from. It's made by recombinant DNA technology, which is really now used to make many drugs. So
I mean, we have it in our bodies. I mean, it's core. You know, when you go to the, not to oversimplify it, but when you go to the gym and you sort of tear a muscle lifting a weight, right? Isn't that how your body sort of starts the recovery process to a certain extent?
In the manufacturing of this kind of thing is incredibly well worked out because there are many drugs that are marketed that are produced in bacteria, for example. So it's highly regulated. It's done in safe manufacturing facilities and things like that.
It comes from commercially. I'm fairly certain that Ajinomoto derives it from a bacteria.
Natural sources of it, but I think Ajinomoto's screened many different forms, and their favorite forms they produce in bacteria.
Yeah, for a long time I believe they were using bovine, but now they're using bacteria.
In furthering your education with these products and some of the techniques you're using, do you worry that in any way you might be sort of stunting the growth of young cooks who sort of fall in love with these things too quickly and aren't learning how to properly roast a chicken like you did and want to come work for you, I don't know, too early or something? Or what are you looking for in young cooks who want to come work for you?
I'm just looking for people with an open mind, people that are willing to think, sort of, period. Do I think that it's a danger that maybe somebody might skip steps in life? Yes, I think that that's something that I would discourage. But it's not like if you come to WD-50 you won't have to roast a chicken or fillet a fish, or everything doesn't come in that little bag I just cut open. It comes whole, and we break it down and fabricate it. There's a lot of classical cooking technique that happens at WD-50. Don't be confused and think that that you're going to miss out on that stuff. You're hopefully going to be see some things you would see at maybe only a handful of other restaurants around the world. But there's also quite a bit of the old blended in with the new, and that's firmly rooted in my approach to cooking, mixing both the old and the new. I don't encourage anyone to skip steps, but I don't think that we're doing that at the restaurant.
How cost effective has the introduction of meat glue been to your restaurant, since you seem to be using a lot of the less desirable cuts of meat?
Less desirable, or maybe more affordable?
There we go.
It's probably a nicer way of putting it. I don't know that there's a less desirable cut of meat. I mean, I think that what's interesting about animals is that they have a lot of flavor to offer for different reasons in different places. I didn't know that the diaphragm would be delicious, but it is, and it's particularly delicious when you can make sort of a chunk out of it. And I don't have the actual hard data on specifically how, from an economic standpoint, how beneficial it's been to us. But I can certainly say that we've just reduced the general amount of waste, particularly with seafood, quite a bit. I'm sorry I don't have hard data on that, but it is very useful in that respect. You just have to trust me on that.